Today's lesson is about graphs, equations, and tables. We're going to be talking about how to represent a geometric relationship, and you'll see what that looks like in a second. We're going to practice writing equations for table, and then using the equations to make predictions. We're going to define what a function is, and also a linear function, and we're going to learn to identify functions. Okay, our first problem is from our textbook, representing a geometric relationship. In the diagram below, what is the relationship between the number of rectangles and the perimeter of the figure they form? Represent this relationship using a table, words, an equation, and a graph. So we have here a series of rectangles. We have one rectangle, and it shows us that the rectangle has a length of 6 and a width of 1. And then we have two of those rectangles put together, 3 rectangles, and 4 rectangles. So I'm going to start by making a table, and on the left side of my table I'm going to have the number of rectangles. Let me just draw a rectangle there. And then in my other column I'm going to have the perimeter of the rectangle, of the resulting shape. So if I have one rectangle, along the long sides I have 6. So I have 6 plus 1 plus 6 plus 1, that's 6 plus 1 is 7, plus 6 is 13, plus 1 is 14, so I have a perimeter of 14. When I have two rectangles, the perimeter does not double. I still have long sides that are 6, short sides that are now 2 wide, so 6, 7, 8, plus another 6 is 14, plus 2 is 16. For 3 rectangles, I have a perimeter of 18. When I have 4 rectangles, I have a perimeter of 20. In order to write an equation for this sort of linear function, we're going to use this series of steps: now, next, change, and start. So we're first going to look at where we are now. So at the bottom, the last set of rectangles that we have to look at, we have a perimeter of 20. If we were to keep going and we were to go to 5 rectangles, the next number would be 22. Because we can see that when we look at our perimeter column, the numbers are going up by 2 each time. So our change is plus 2. Now let's take a look at what this looks like over on the graph. Along the x-axis, I'm going to put my independent variable, which is the number of rectangles, and on my y-axis I'm going to use the perimeter of the rectangles. For number of rectangles, I'm just going to label by ones. For perimeter, I'm going to go by 4, so I'm going to go 4, 8, 12, 16, 20, 24, and that should be as far as I need to go. Okay, so when I have one rectangle, I have a perimeter of 14. So that's my first ordered pair. 1, 14. When I have 2 rectangles, I have a perimeter of 16. 3 rectangles, I have a perimeter of 18. 4 rectangles, I have a perimeter of 20. And as we already saw, if I had 5, it would be 22. Oops, because this forms a line, it would just keep on going. 6 would be 24. And now, if I go back over here to my now, next, change, start. By start, what I mean is, if I were to keep going and I were to draw a line tracing these dots, where would I end up? We can see from the graph, I would end up right here at 12. So my start, when x equals 0, y equals 12. Now that's not actually possible. We can't actually have a perimeter if we have 0 rectangles. But if we're looking at the pattern, as we're going up by 1s, the perimeter is going up by 2s. So if we were to go backwards 1 to the number 0, the perimeter is going to be 2 less, which is 12. Now, of course, that's an impossible situation, but it does give us an equation that works. Every linear equation that we write is going to be in this form. Y equals the change times the variable x, which is our independent variable, plus start. So our number of rectangles is our x. Perimeter is our y. So the perimeter is going to equal the change, which is positive 2, times x plus that starting value, which is 12. And this is going to work for every column in the original table. So if we go to the second column, if we put 2 in for x, we have 2 times 2 is 4, 4 plus 12 is 16, and that's what y is when x equals 2. Similarly, for x equals 3, if we put 3 in for x, we have 2 times 3 is 6, 6 plus 12 is 18, and that's what y is when x is 3. So that's an easy way to find what our formula is for any line. Let's take a look at the next example. This is one for you to try, so take a couple minutes, try this on your own, and then pause the video and come back and check your answer. Okay, I'm going to set up the table for this one pretty much the same way I did the last one. This time I'm going to have the number of triangles, and then I'm going to have the perimeter of the triangles. I'm just going to use the letter P. So for one triangle, I have a perimeter of 10, because 3 plus 4 is 7, and 7 plus 3 is 10. When I have two triangles, I have to find just the distance around the outside. 3 plus 4 is 7, plus 3 is 10, plus 4 is 14. For 3 triangles, I have a perimeter of 18. For 4 triangles, I have a perimeter of 22. So right now, my perimeter is at 22. If I were to go to the next value, you can see that my perimeter is going up by 4 each time. So adding 4 would give me 26. My change is plus 4. And my start is what it would be if I went backwards 1. So when I have one triangle, I have a perimeter of 10. If it were possible to have 0 triangles, I'd be going back 1 in the x column. So I would go back by 4 in the y column. 10 minus 4 is 6, so my start is 6. So I have y equals the change, which is 4, times x plus the start. Over on the graph, I have number of triangles as my independent variable and their perimeter as my dependent variable. Again, I'm going to number by ones for my triangles. And I think I'm going to go by, I'll go by 4s again. So 4, 8, 12, 16, 20, 24, and let's go one more. Let's go to 28. Okay, so when I have one triangle, that's a perimeter of 10. Two triangles is a perimeter of 14. 3 triangles is a perimeter of 18. 4 triangles is a perimeter of 22. And it looks like that. And we talked in class about we would not draw a line connecting these points, because if we drew a line, that would mean we could have a value for 1.5 triangles, which is not possible. So we're not going to actually draw the line, but we could trace a line to predict future values, as long as we keep in mind that we can only have whole number values for x. Okay, objective 2 is to write an equation for a table and use the equation to make predictions. So we're going to use our equation now to stretch beyond the information given us to make predictions about future events. Team Renaissance will be traveling to the Happy Mohawk Canoe Livery to take a canoe trip. The bus will cost $600 to get us there. Each person traveling in a canoe will cost $13. How much will it cost the team to take a class of 30 students? So our table only goes up to 4 students. We want to know how much it's going to cost to take a class of 30 students. So if that were just 5 or 6, we might just keep going with the table, but it's helpful to have an equation when we're projecting a value far beyond values that were given. So right now, if we look at our cost, right now we're at $652. To figure out what our next value would be, we're going to look at how far up it goes from one number in the table to the next. So if we go from 613 to 626, that's a change of plus 13. 626 to 639 is also plus 13. And this is also plus 13. So it has a constant change. That tells us that it's a linear function, and we're adding 13 each time. So if we add another 13, our next number is going to be 665. So that's our next 665. Our change is plus 13. And start is what would happen if we had 0 people. So if we go back to 0, we're going to subtract 13 to get from this value to the previous value. We get a value of 600. So our start is 600. And it actually tells us that in our original problem. It says the bus will cost $600 to get us there. So it's saying we're paying $600 for the bus, plus we're paying $13 per student. So we have y equals the change times x plus start. And this makes sense. We have $13 per person, 13 times x, plus the $600 fee for the bus. And we could actually find out what the cost would be, because it did ask us how much will it cost the team to take a class of 30 students. So when x equals 30, what is y? When x equals 30, y equals question mark. So I'm going to substitute this 30 in for x. Y equals 13 times 30 plus 600. 13 times 30 is 390. And we still have plus 600. So y equals 990. So it is going to cost the team $990 to take a class of 30 students. Our third objective is to define function and linear function. In the previous shape problems, the perimeter of the figure was a function of the number of shapes. A function is a relationship that pairs each input value with exactly, and underline that because that's an important word, with exactly one output value. So there was exactly one perimeter for each number of shapes. We didn't say, well, there's 2 triangles, so the perimeter is either this or this. The perimeter is only one thing if we had 2 triangles. Let's get a little more specific now. A linear function is a function whose graph is a straight, non-vertical line or line segment. So any line is a linear function as long as its graph is not vertical. So vertical going up and down. We cannot have a vertical line segment. And we'll see why that's true a little bit later. A linear function will always have the same rate of change. So as we saw in our tables, we added on the same amount each time. It changed by plus 2 in our rectangle example. It changed by plus 4 in our triangle example. It changed by 13 in our canoe example. Okay, let's take a look at why it cannot be vertical. So let's draw a vertical line. Let's label our x-axis. Whoops, I don't want a 0 there. Okay, fix that. I'm going to go just by ones. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4. We'll just go up 6 here as well. Okay, I'm going to draw a vertical line right here. Now for this vertical line, when x is 4, which is the only thing x can be because there aren't any other points. When x is 4, y could be 1, or it could be 2, or it could be 3. It could be anything. It could be absolutely anything. So each input does not have exactly one output. When we input a 4, we get numerous different outputs. So that's why a vertical line is not considered to be a linear function. Okay, this example may help you determine a little more, understand more what a function is. A certain business, okay, was interrupted by a phone call there. Certain business keeps a database of information about its customers. Is home phone number a function of customer name? Okay, so what it's asking us here is, does every customer name have just one phone number? And we see here, Heather Baker has a phone number, Mike London has a phone number, Sue Green has a phone number, Bruce Swift has a phone number, Michelle Metz has a phone number. Heather Baker only has one phone number. She does not have more than one. She does not appear more than once on the list. Mike London only has one phone number. Each customer only has one phone number listed. So the answer is yes, because each customer name has only one phone number. Now let's go backwards. It asks us if customer name is a function of home phone number. So we have this home phone number, and it belongs to Heather Baker. Now we have another phone number, which belongs to Mike London. We have this phone number, which belongs to Sue Green, and then we have the same phone number as for Sue Green that also belongs to Bruce Swift. So they share the same phone number. When we put in this number, we don't know if we're calling Sue Green or Bruce Swift. So customer name is not a function of home phone number. And then number 3 asks us to explain why a business would want to use a person's social security number as a way to identify a particular customer instead of their phone number. So if you think about this, every person has their own unique social security number. So we don't share a social security number with anyone, we have our own, whereas people do share phone numbers. At least they did back in the day when people used home phones. Some people still do. Nowadays with cell phones, people do tend to have their own phone number, but it used to be that if multiple people lived in the same household, they might all share a phone number. Okay, let's look at some more examples to make this a little more clear. Is it a function? And then if so, is it a linear function? So looking at our first example, we have x equals 1 and y equals 1. And then we have when x equals 1, y equals 2. That's a problem because we don't know what y is going to be when x equals 1. Each input does not have its own output. This time, x equals 1 means y equals 1, and this time x equals 1 means that y equals 2. So no, this one is not a function at all. Okay, let's look at this one. X equals 0 goes to y equals 6, 1 goes to 10, 2 to 14, 3 to 18. Each x value has its own unique y value, so yes, this is a function. To see if it's a linear function, we see if it goes up by the same amount each time. The y value goes up by 4, plus 4, plus 4. It has a constant rate of change, so yes, it is also a linear function. And we could go ahead and use our now next change start. Now we're at 18. The next value would be 22. We have a change of plus 4, so y equals 4x. And we actually have the start value right here on the graph. When x is 0, y is 6. So we have 4x plus 6. Okay, the next one, 0 goes to negative 2, 1 goes to 4, 2 goes to 2, and 3 goes to negative 2. There are no duplicate x values. Each x value has only one y value, so yes, it is a function. Now let's see if it's a linear function. If it goes up or down by the same amount each time, it would be a linear function. This goes up by 6. Now it goes down by 2 and down by another 4. So it does not have a constant rate of change. It is not a linear function. Let's look at the last example. For x equals 0, y equals 1. X equals 1, y equals 3. X equals 2, y equals 5, and x equals 5, y equals 11. There are no duplicate x values. Each x value has a unique y value, so yes, it is a function. Now let's look to see if it goes up by the same amount. 1 plus 2 is 3. 3 plus 2 is 5. And 5 plus 2 is not 11. But if we look at what's going on with our x value, it skips from 2 to 5. So we have to kind of imagine values 3 and 4 in here. We'd have 2 plus, or 5 plus 2 would be 7. And then 7 plus 2 would be 9. And another 2 would be 11. So even though this may not at first appear to be a linear function, it's still going up by 2 each time. So yes, it is a linear function. The change is 2. And we know our start value when x is 0, y is 1. So we have 2x plus 1. Okay, this is exit ticket that would be done in class. We're not going to go over it on this video. This is your assignment. You're going to do 6 through 13 in your textbook. I would like you to list the now, next, change, and start to write your equations, and also graph your equations. Thank you for watching.